sounds
The
good.
next talk is on sum of squares meets square laws, fast rates for agnostic tensor completion, and Dylan Foster will give the talk.
Thanks. Cool. Yeah, so this is a talk about efficient algorithms for tensor completion of the agnostic model. It's work with Andrei Ristevsky. So let me describe the problem. So in tensor completion, we have an unknown low-rank tensor, and our goal is to recover the tensor from a small number of observed entries. Okay, so for this talk, when I say an unknown tensor, what I mean is, just a d by d by d array, so like a 3 tensor. And by low rank, we just mean that it decomposes as the sum of a small number of rank 1 components. So, if you're familiar with the classical matrix completion task, this is just a natural higher order generalization. But we're actually going to depart from this model a little bit in this talk, and what we'll work in is the agnostic version of the problem. So here, instead of assuming the tensor is low rank, we make no assumptions, but we would like to predict the entries well, as well as the best low rank tensor. So what this means, is if y does turn out to be low rank, we'd like to have good error. If y is complete noise, maybe we won't do so well, and in general, we hope to get like a nice interpolation between these two regimes. So the way we'll formalize this is as a special case of a general tensor regression framework. So here we're going to get n feature target pairs IID, and features for us are just d by d by d tensors. And for any particular tensor, we'll just measure risk via squared prediction error for the targets. And what we'd like to get is an excess risk bound. So we'd like to produce a predictor t hat where its loss is small relative to the loss of the best rank R tensor. Okay, and the tensor completion setup, this is just a special case of this where the observations are just random indicators for the entries we've observed. Okay, so let's first look at what rates are possible for this setting. And here it's first helpful to think about what's just possible information theoretically. So here, if we focus on the case where rank is 1, it's well known that there's an inefficient algorithm that gets a rate of d over n. So d is sort of the natural parametric rate, and we expect a 1 over n rate because we're working with square loss here. But when you go for efficient algorithms, things get a little bit more interesting. Here it's helpful to think about what happens in the matrix case. So in the matrix case, you can do least squares with a nuclear norm penalty, and this allows you to kind of have your cake and eat it too. So you get the d over n rate, and you get this with an efficient algorithm. But unfortunately for tensors, as soon as you go above order 2, the tensor nuclear norm is computationally intractable, even to approximate. And so we need to think about other algorithms. This approach won't work. One natural thing you can do is just reduce to tensor completion by flattening your tensor. But this gets worse dependence on d. So this gets d squared, and that's sort of like a natural barrier for matrix completion methods. But interestingly, Brock and Moitra in 2016 showed how to get beyond this barrier. So they give a rate that becomes non-trivial as soon as n is at least d to the 3 halves. Okay, so that's better than d squared. And interestingly, it's probably unlikely that you can get better than d to the 3 halves under standard hardness assumptions. But what you notice about this bound is that it's what we'll call a slow rate. So if you look at the inefficient algorithm, this was going down as 1 over n. And this one is only going down at a rate of 1 over root n. So our main contribution is to give an efficient algorithm that gets the natural fast rate analog of this result. So we get a rate of d to the 3 halves over n. So in a little bit more detail, our main theorem is the following. So we show that if you do least squares with a constraint based on a sum of squares relaxation for the tensor nuclear norm, then your risk relative to the risk of the best rank R orthogonal tensor goes as d to the 3 halves over n with a polynomial dependence on R. At a more conceptual level, sort of the key thing we show here is how to make sort of the usual localization arguments that are used to prove fast rates in high dimensional statistics. We show these play nicely with the sum of squares relaxations. So basically, whenever you try and prove fast rates for convex relaxations, sort of the key abstraction to think about is what's called localization. And essentially what this is it says that if you, when you're proving generalization error bounds, you kind of only need to look at tensors that are close to the optimal predictor. So we show how to make these arguments work for, for SOS in this setting, essentially. And beyond this, we show how to extend this to some other measurement models, and we also give another hardness lower bound, which essentially just says that if you believe standard CSP hardness assumptions, you probably can't improve this d to the 3 halves factor by much. Okay, so in the remaining time, I'll just talk about the algorithm and its analysis in a little bit more detail. So the starting point for the algorithm is to look at the tensor nuclear norm. And this is essentially just looking at what is the minimum weighting that allows us to write our tensors as sum of rank 1 components. But it's a little bit more helpful to think about this just in terms of the dual norm, which is the injective tensor norm. That's really just the operator norm for the tensor as an operator on rank 1 tensors. So this is intractable to compute, but what you can do is the sum of squares relaxation. And all you really need to know about this for this talk is that sum of squares defines a sequence of relaxations of the norm, the injective tensor norm, parameterized by a degree k. And so these approximations get tighter as k gets larger at the cost of more computation. So our algorithm is just least squares subject to a constraint on the dual of the injective tensor, or of the SOS injective tensor norm. This is what I call the SOS nuclear norm of degree k. So how do you analyze this? So let's define T star to be the best fitting rank R tensor, and we'll define script T to be a set of what we'll call like feasible estimators that come out of our least squares procedure. So these just have small SOS nuclear norm relative to T star. So there's two parts. So the first part is to show that your generalization error is bounded by what's called like an offset Rademacher process. So this has one term that looks like the usual kind of uniform convergence, but it has a negative quadratic offset that's sort of trying to cancel this statistical deviation term. And so we want to show that it cancels it enough. And this is where we need new arguments for SOS. And this is really where this idea of localization I was talking about comes in. So there's 3 steps. And so the first step is just to observe that this Rademacher term scales as sort of like a statistical term times the SOS nuclear norm of the difference between the tensor we're considering and the optimal tensor. And the difference in subscript here from 6 to 4 is intentional. So the second step is to give what's called like a norm comparison inequality. So this is a new lemma. And so what we show is that for the feasible tensors that arise here, you can pay a factor of rank to move from the SOS nuclear norm to the Frobenius norm. So it says in a certain sense, the feasible tensors are approximately low rank. And then the third step is to give what's like called a restricted eigenvalue guarantee. And this shows that if you look at the Frobenius error here, this is proportional to the empirical squared error. So if you chain all these inequalities together, what they say is that this first Rademacher term arising in our generalization bound, this is basically proportional to the offset term, and so you get a cancellation, and this leads to the 1 over n rate. So let me just describe these technical tools in a little more detail. So there's 2 tools. The first is this norm comparison inequality, and the second is this restricted eigenvalue guarantee. And we're sort of most excited about the norm comparison here because this requires a new characterization for what does the subgradient of the SOS nuclear norm look like. So that's sort of like the key tool, and I imagine this may have applications in other settings. So once you have this, you can prove this restricted eigenvalue guarantee essentially by using concentration guarantees we already had for the SOS nuclear norm, plus some sort of standard peeling arguments, and by using this norm comparison itself. Okay, so that's the result. To summarize, we have the first efficient algorithms that beat this d to the squared barrier for agnostic tensor completion and get the fast rate. And these are via some new geometric inequalities for SOS. But sort of conceptually, the main takeaway here is that like these SOS relaxations, these play nicely with the usual high-dimensional statistics analysis, and I think it'd be nice to see the extent to which this works for other models and other relaxations. So thanks.